math video lesson on polynomial functions. In today's lesson, I'm going to walk you through all the major ideas you need to understand polynomials, how to describe them, how to graph them, how to solve them, and how to apply them to real-life problems. By the end of this, you should have a solid understanding of how polynomial functions behave and why they're so important to algebra. Here's an overview of what I'll be talking about. Part 1 will introduce the key vocabulary and concepts that we will rely on throughout the presentation. These include things like end behavior, turning points, multiplicity, and the rational root theorem, and more. Part 2 will feature detailed examples of graphing and analyzing different types of polynomial functions. I will walk you through a quadratic, a cubic, quartic, and quintic function and show you what makes each type unique. Part 3 focuses on solving. I'll explain and demonstrate important algebraic terms like factoring, the rational root theorem, and synthetic division. Finally, Part 4 will be a real-world application problem where we can use a polynomial to solve for the dimensions of a flower bed. Let's get started with the vocabulary. There are several important concepts we need to understand. First, the polynomial degree determines the overall shape of the graph and the maximum number of turns it can have. Next, the leading coefficient controls the direction of the arms of the graph, meaning whether the end rises or falls. End behavior is determined by the leading term, and it describes what the graph does as x approaches positive or negative infinity. Turning points are the places where the graph switches direction, and a polynomial of degree n can have up to n-1 turning points. Multiplicity explains how the graph behaves at each root. It tells us whether the graph crosses the x-axis or if it just touches and bounces off of it. We also look at absolute maxima or minima, which are the highest or lowest y values the graph reaches overall. And finally, local maxima and minima are the smaller peaks and valleys on the graph that aren't necessarily the highest or lowest points. And concepts. First, the rational root theorem helps us predict all possible rational zeros of a polynomial by using the factors of the constant term over the factors of the leading coefficient, also called P over Q. Next, the factor theorem says that if f of c equals 0, then the binomial x minus c is a factor of the polynomial. Similarly, the remainder theorem tells us that when we divide a polynomial by x minus c, the value of f of c is the remainder of that division. Synthetic division is a shortcut method that allows us to divide a polynomial by a linear binomial faster than long division. For the sums of cubes and difference of cubes formula, you can just look at the slide. The formulas are written there for reference. We also use factor by grouping, which is an advanced technique to factor certain polynomials that don't factor easily in one step. And finally, polynomial long division is used to divide higher degree polynomials when synthetic division can't be used. Our first example is the quadratic function 3x squared plus 4x minus 4. Using factoring or the quadratic formula, we find these zeros at x equals negative 2 and x equals 2 over 3. Both have multiplicity 1, so the graph crosses the x-axis at each intercept. The y-intercept is found by substituting in x equals 0, which gives us negative 4. Because the polynomial has an even degree and a positive leading coefficient, both ends of the graph rise towards positive infinity. The graph has one turning point because quadratics can have at most one. This turning point is a minimum at y equals negative 16 over 3. The graph is decreasing until x equals negative 2 over 3 and increasing after that. Altogether, this is a smooth, continuous U-shaped curve with no absolute maximum, but one absolute minimum. Our next function is the cubic x cubed minus 3x squared plus 4x minus 12. This function has a single real zero at x equals 3, which gives us the x-intercept 3, 0. The other two solutions are complex numbers. The y-intercept is 0, negative 12. The cubic functions have odd degree, so they fall on one end and rise on the other. This particular cubic rises to infinity on the right and falls to negative infinity on the left. This graph is always increasing, meaning it has no turning points. There is no local maxima or minima, and the graph passes smoothly through the intercept at x equals 3. Our quartic function is x to the fourth minus 6x cubed plus 11x squared minus 6x. This polynomial factors nicely into x times quantity x minus 1 times quantity x minus 2 times quantity x minus 3, giving 4 real zeros at 0, 1, 2, and 3. All of these have multiplicity 1, so the graph crosses at each intercept. The y-intercept is also at 0, since substituting in x equals 0 gives us 0. Because the degree is even, both ends of the graph rise towards positive infinity. The quartic has 3 turning points, which is the maximum possible for a fourth degree polynomial. It has a local maximum at approximately 0.5625 and a local minimum at 1. There is no global maximum, but the graph does have a global minimum value of 1 along the curve. The last graph in this section is the quintic quantity 3x plus 4 to the fifth power. This polynomial has a single real zero at x equals negative 4 over 3. Because the multiplicity is 5, which is high and odd, the graph crosses the x-axis but flattens slightly as it passes through the intercept. The y-intercept is extremely large. When x equals 0, we get 1,204. Quintic functions have an odd degree, so the left end of the graph falls and the right end rises. This particular graph behaves similarly to a stretched out cubic, but with a much sharper rise due to the fifth power. Now let's apply some solving techniques. For the polynomial p of x equals to x cubed minus 9x squared plus 23x minus 15. We start by listing all the possible rational roots, which is plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Using synthetic division, we test these values. We find that x equals 1 is a root. Dividing the polynomial by x minus 1 gives us a quadratic. Testing again, we find x equals 3 is also a root. Dividing again gives us a linear factor. Finally, we find x equals 5 is the last root. So the polynomial has zeros at x equals 1, x equals 3, and x equals 5, all with the multiplicity of 1. Our next example involves factoring a fourth degree polynomial 27x to the fourth plus 54x cubed minus 64x minus 128. We use factoring by grouping to rewrite as 27x to the third times quantity x plus 2 minus 64 times quantity x plus 2. We then factor out the common binomial x equals 2, quantity x plus 2, leaving us with quantity x plus 2 times quantity 27x to the third minus 64. The remaining expression is a difference of cubes, since 27x to the third equals 3x to the third, and 64 is equal to 4 to the third. That lets us factor further into quantity x plus 2 times quantity 3x minus 4 times quantity 9x squared plus 12x minus plus 16. The quadratic has complex roots, complex roots, but the two real zeros of the entire expression are x equals -2 and x equals 4/3, each with a multiplicity of 1. To determine whether a binomial like quantity x plus 2 is a factor of a polynomial, we use the remainder theorem. Look at the slide for the definition. We substitute x equals -2 into the original function, which is p of x equal to x cubed plus 2x squared minus x minus 2. If p of -2 equals 0, then the remainder is 0 and the binomial is a factor. Using synthetic division confirms this result. The remainder comes out to 0, proving that quantity x plus 2 divides the polynomial evenly. Finally, let's look at a real-world application involving a raised flower bed. Pause the video to read the question. We are told that the outer length of the bed is 4 times the height, the outer width is 2 times the height, and the boards on the sides have thicknesses of 4 and 6 inches. The boards also rise 4 inches above the soil. We let h be the height of the entire bed. That means the outer length is 4h and the outer width is 2h. Next, we subtract the board thickness to get the inner dimensions. The inner length is equal to 4h minus 12. The inner width is equal to 2h minus 8. And the inner height is h minus 4. Of the soil inside the bed must be 3,136 cubic inches. So we form the equation quantity 4h minus 12 times quantity 2h minus 8 times quantity h minus 4. We begin by simplifying by factoring out common terms. We rewrite the expression as 4 times quantity h minus 3 times 2 times quantity h minus 4 times quantity h minus 4. Multiplying the constants give 8, so we get 8 times quantity h minus 3 times quantity h minus 4 squared. Dividing both sides by 8 gives us quantity h minus 3 times quantity h minus 4 squared is equal to 392. Next, we expand by simplifying the polynomial and eventually reaching at h cubed minus 11h squared plus 40h minus 440 equals 0. Factoring this gives us h squared plus 40, quantity h squared plus 40 times quantity h minus 11 equals 0. The quadratic cannot give us real solutions, so the only meaningful answer is h equals 11. We have the height. We can find the outer dimensions. Length is equal to 44 inches. Width is equal to 22 inches, and the height is equal to 11 inches. So the final dimensions of the flower bed are 44 inches by 22 inches by 11 inches.